Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. Now let's look at the graph theoretic characterization of primitive matrices. Okay. Before we do that, we introduce something that's known as a Frobenius number. So let's see what is a Frobenius number. We start by considering a set of positive numbers given by S. The set S consists of n numbers starting from S1 up to Sn. Okay. Then we say that an integer m is representable by S if there exists a set of non-negative integers alpha 1 to alpha n. Note that these are non-negative, meaning 0 is included, such that we can express m as a linear combination of the numbers S1 to Sn, where the coefficients are nothing but the non-negative integers alpha 1 to alpha n, as written here. Okay. Now, say we have a set of numbers S1 to S1. In that case, there often exists a largest unrepresentable integer, and that integer is what is known as the Frobenius number of the set S. Okay. And when does the Frobenius number exist? It only exists when the greatest common divisor of all the numbers in the set S, which is small s1 to small sn, if their greatest common divisor is equal to 1, only then we can find such a number. Let's quickly see an example. Suppose we assume that the set S that is given to us consists of two numbers 3 and 5. Let us try to find out the Frobenius number of 3 and 5. Remember, Frobenius number is the largest unrepresentable number. Okay, so let's start. So 0 can be expressed as this. Now 1 cannot be represented irrespective of whatever alpha 1 and alpha 2 we put here. Similarly, 2 is not representable for any values of alpha 1 and alpha 2. 3 is an easy one, we can simply write this. Now again, 4 cannot be represented. The number 5 again is an easy one, and we can simply write this. Similarly, 6 can be written as this. 7 again cannot be represented. 8 can be represented as this. 9 again is an easy one. 10 also. And 11 is, this should be 5. So notice that any number which is larger than 7, any number larger than this will actually be able to represent it using the numbers 3 and 5, meaning that the largest unrepresentable number of the set S, which is, in other words, equal to the Frobenius number of S. This is equal to 7, meaning any integer larger than 7 can actually be represented using the numbers 3, 5, and we can quickly also check that the GCD of 3 and 5 is equal to 1. So our claim that a Frobenius number must exist holds here. Okay. So where do we actually use the notion of a Frobenius number? In order to understand that, we need to introduce or talk more about how walks of various lengths can actually be created using the cycles in a digraph. So let's see how that goes. Now, let us consider a digraph which is strongly connected. Which is strongly connected. This implies that G has at least one simple cycle in the digraph. In the digraph. Okay. Now, let's talk a little bit more about these cycles in the digraph. So, we say, suppose G, which is strongly connected, so in the interest of time, I'll just write this abbreviation, which is strongly connected, has a set of n simple cycles. Up to Cn. Of lengths L1 to Ln. Okay. Now, since G is strongly connected, we know that there exists a directed walk from every node to every other node. So, there exists such a walk from every node to every other node. Now, let us look at some examples and try constructing some walks using the cycles in the digraph. Suppose we consider this digraph now. What is the number of simple cycles here? As we can see, there are two simple cycles. One is this and the other one is this. So, let us write down what the cycles are. It is and C2 is equal to 5 and then back to 3. Okay. So, suppose we try to construct walks now starting from node 1 to the node 3. Now, let us see what are the lengths of all of the walks that we can construct. Let's try to do that. Okay. So we can see that the smallest possible walk goes like this, 1 to 2 to 3. But now notice that we also have the cycle C2, which we can now use to generate longer walks, meaning, so this walk has a length equal to 2, but now I can also do this. And then back to 3, meaning I have traced a walk now of length 5. Similarly, so in this case, we traversed along the cycle C2 just once, but now I can keep doing it repeatedly to generate walks of lengths given in this form, 3i, where I is simply the number of times the cycle C2 is traversed. Okay, so this is how we can use the cycles to actually generate walks of longer lengths. But let us notice something more here. So we observe that the graph is actually strongly connected, and we can generate walks which are quite long, stretching up to infinity, say. But can we actually generate walks of arbitrary lengths? For example, let us say we are trying to generate a walk of length 7. Can we do that using the cycle which is given here? So, this is a task for the students. Please pause the video here and try to generate a walk starting from 1 and ending at node 3, which is of length 7. So, you will observe that it is not possible to do that, even though the network is strongly connected. That means clearly strongly connectedness is not enough when we want to generate walks of desired length. So, let us note that down. Walks of, let us say, any arbitrary length. So, now the question is, what more does the digraph need so that we can actually start generating walks of arbitrary lengths? Or let us simplify the question to the particular example that we saw here. Now, is there a way in which we can actually modify this particular digraph, the one shown here, such that we can start generating walks of desired length? So, the answer is yes, it is possible to do that. So, let us see how we can do that. Okay. So, we now have the same digraph that we had there. Let me add a few more nodes here. And let us number them So what we have actually done here is we have added a new cycle to the diagram. So let's write up again all the cycles. So we had 2 cycles from here. Let's call them as shown here. Let me take this information as well. Okay. So now the number of cycles in the network has changed from 2 to 3, and one more cycle has gotten introduced, which is this. So what is the third cycle? It is equal to 2 to 6 to 7 to 8 to 9 and then back to 2. So it is now a cycle of length 5. So we see that the network has 3 cycles now. So can we now possibly use this new added cycle along with C2 to generate walks of arbitrary lengths? Let's try to answer this. Again, let's check if the network is strongly connected or not. Yes, it is still strongly connected. So do longer walks exist? Let's see. So now we are trying to generate walks again from node 1 to node 3 by traversing both the cycles C2 and C3, meaning the lengths of the walks can be represented in this manner. L is equal to 2, which is the distance from here to here, plus the length of the cycle, so length of the cycle C2 plus again the length of the cycle C3, and we know what is the length of C2, it is equal to 3. So we can write 3 alpha 1 plus 5 alpha 2. 5 is the length of the cycle C3, and what is alpha 1 and alpha 2? So alpha 1 is simply number of times the cycle C2 is traversed, and similarly alpha 2 is the number of times C3 is traversed. Okay. So now let's focus a little bit on this particular expression. So what are we doing here again? We are again trying to look at all the possible lengths, which are again integers, that can be represented using the numbers 3 and 5. And we already have an answer to what are the numbers that we can represent. So let me take you back to this example where we saw that the largest representable number of the set 3 and 5 is equal to 7, meaning any length greater than 7 can actually be represented using the numbers 3 and 5, meaning this implies L greater than 2 plus 7, any L greater than 2 plus 7 is actually reachable through the walks generated using C2 and C3. Meaning any walk of length greater than 9, strictly greater, can now be generated using the 2 cycles. Notice this was something which was not possible in the previous digraph, even though it was strongly connected. So meaning now all that we need to do is need to have cycles whose GCDs are equal to 1, the lengths. So, let us write it here. We notice that the GCD of 3 and 5 is equal to 1. Because of the presence of a cycle which has such suitable lengths, we were able to generate walks of arbitrary lengths. So, let us summarize the result that we have. Let G be a weighted digraph with nodes greater than equal to 2. And a weighted adjacency matrix. Matrix A. Then the following statements are equivalent. So, what are the two statements? The first one says G is strongly connected and aperiodic. So, what is an aperiodic graph or digraph? Now, in an aperiodic digraph, the GCD or the greatest common divisor of the lengths of all of the cycles is simply equal to 1. We know that in such cases a Frobenius number exists. Okay. Now, if the network is strongly connected and aperiodic, then the adjacency matrix A is primitive. So, now we know what is a graphical representation of the notion of a primitive matrix. So, if the adjacency matrix is primitive, then the underlying graph becomes strongly connected and is aperiodic. So, this brings us to an end to the discussion on the graph theoretic characterization of the adjacency matrix. In the next lecture, we will talk about the spectral properties associated with the adjacency. Thank you.